abstract domains. It is often the rare categories that are of great interest in various applications, such as network intrusion detection in computer networks, emerging trend detection in social networks, and money laundering detection in online transaction networks. As a result, rare category characterization becomes a fundamental learning task, which aims to accurately characterize the rare categories given limited label information. The first unique challenge of rare category characterization comes from the highly skewed data distribution. For example, in 2012, Snapchat only had 30 million users while Facebook had 1 billion users, which makes it challenging to identify such emerging social network like Snapchat in the real scenarios. The second challenge is non-separability nature of the rare categories from the majority classes, as the communities are often non-separable in the real-world networks. The last one is the availability of the multimodal representation of the examples, such as the topology features and attribute features. Traditionally, the rare category characterization paradigm can be separated into a two-step process. In the first step, we aim to identify and extract structural patterns and topology features, which corresponding to the feature engineering step. In the second step, we usually need to design certain types of data mining and machine learning model to capture the rare category patterns. What if you can jointly model the underlying two tasks in a mutual beneficial way? Will that be cool? In this paper, inspired by the family of curriculum learning, we propose a self-paced framework named SPARC that gradually learns the rare category-oriented network representation and the characterization model in a mutually beneficial way. In particular, SPARC stands for Self-Paced Rare Category Network Representation and Characterization. A simple but useful way to evaluate the network representation approaches is to visualize the network layout in the embedding space. On the left hand, we have the network layout of the original graph, while on the right hand, we compare our proposed SPARC algorithm with 3 state-of-the-art network embedding algorithms, including 2 unsupervised methods, that is, deep walk and line, and 1 semi-supervised method, that is, planetoid. To better illustrate our model, on the left hand, we show the underlying learning process, and on the right hand, we show the vertices that were selected by the self-paced learning for training on the final embedding space of SPARC. For the self-paced learning process, we mainly have 3 stages. In the first stage, SPARC extracts the graph context and nodes attributes for the feature learning model and rare category prediction model. The second stage is the key step of our proposed SPARC model, which jointly selects the rare category-oriented graph contexts and reliable based on the self-paced learning scheme. In the third stage, the newly extracted graph node context pairs and labeled rare category examples are fed into the feature learning model and prediction model for the training purposes. Over the learning paces, we observe that our proposed SPARC algorithm focused on extracting rare category-oriented graph context and preserve them in the red circles. In such way, we can better capture the context information of the rare examples than the existing network embedding approaches. Please make sure to check our paper and open source code on the author's websites.